This is going to be kind of a review of Chapter 3, Section 1 of our statistics book, talking about scatterplots and correlation. And we've talked about, up to this point, different ways that we can represent data. We've looked at histograms, we've looked at bar charts, bar graphs. We've looked at pie charts, which deal with parts of a whole. We've looked at box plots, dot plots, stem and leaf plots, and we've talked about when each of those is the best way to represent your data. And now we're going to look at scatter plots. And so what scatter plots do is they create a visual of raw data, and we're able to actually measure this raw data, make inferences about this raw data, and we actually can calculate if these two quantitative variables that we're going to be comparing, because that's what we're going to compare is two quantitative variables, are related or associated. So association, correlation, but we also are going to be able to determine how strong or weak the correlation is or the association, and if it's a positive or a negative correlation or association. So let's go ahead and move on and kind of look at the key points of the chapter. So we have identifying our two types of variables. We're going to talk about the explanatory and the response variable. We're going to make a scatter plot, and I'm going to show you how to do that on the Inspire. And again, that's highlighting between two quantitative variables. You can see right here, it's between two quantitative variables. And if I could draw a straight line, that would be fantastic. So we've got two quantitative variables here. We're going to describe the direction, form, strength, and relationship displayed in the scatter plot. Remember, all of these things, we have little acronyms. Remember, we talked about SOCs when we were initially looking at a density curve or a normal distribution or a skewed distribution. We were talking about shape, outliers, measure of center, and spread. So those are the four that we talked about. And we use SOCs. Sometimes it's CUS, just, anything. CUS is a center, measure of center. Anything that's unusual, measure the shape, and the measure of spread. So anyway, there's a lot of different things that we could get into here, but let's focus. We're going to describe the direction and form and also the strength of the relationship, because correlation can be strong or it can be weak. And we can be moderately strong, moderately weak. We're going to kind of look at all those levels. We're going to interpret the correlation. What is it that our number is telling us? And we're going to understand the basic properties of correlation, including how it's influenced by outliers, those pesky outliers. They're always causing problems. We're going to use the technology. I'm going to demonstrate to you how to do this on the Inspire. And then we're going to explain why just because two things are associated doesn't necessarily mean that one causes the other. And we've talked about that a little bit in class. So let's move on to the first part. We have two types of variables. We have the response variable and we have the explanatory variable. Response and explanatory variables, the response variable is our outcome. That is what we are measuring. That's our outcome. The explanatory variable is something that helps explain those outcomes. That's the one that we're basing our outcomes upon. It's the one that may help explain or influence changes in the response variable. And you'll see that we have a representation of this in the next slide. You'll see what we're talking about. But these are your two types of variables. And obviously, both of these are quantitative. And you've got to remember that both of these are quantitative. And I have no idea why my pen is so thick. It's just one of those days. So hopefully you can read my scribbles. But both of those variables are, in fact, quantitative. So let's look at an example. So when we make a scatter plot, we're going to be comparing two quantitative variables, the explanatory variable and the response variable. So what we need to look at is identifying which one is the explanatory and which one is the response. Now, when we talk about correlation, you can have either variable be the explanatory or the response, because the correlation is going to give you a same value. Correlation is blind to whether the label is explanatory or response. The correlation is simply going to tell you, are the two variables, regardless of their assignment, explanatory or response, are they correlated? Are they associated? So when we make a scatter plot, you guys have seen scatter plots before. This is nothing new. A scatter plot is something where you actually put You have a bunch of data, and all you're doing is plotting points. And I'm going to show you an example of that right now. So this is an applet that we used in class, and this is an opportunity to create a scatter plot. Now, the way the scatter plot works is you've got an x-axis and a y-axis, and we'll show some examples of this a little bit later. But if I'm adding data points, scatter plots are exactly as they sound. They're scattered. They can be like me, scatterbrained, but scatter plots are going to be all over the place. Some of them have a very discernible shape, and some of them don't. And we're going to determine how closely related those data sets are, and that's what we're going to use the scatter plot for. So let's go ahead and go back over here. So when we're looking at, first of all, describing the explanatory and the response, because even though that's not really important when we present data based on an R correlation, we still need to have it. Because when you are trying to explain your data and justify your findings, especially when we do experiments, sampling, and you're trying to get your data together, make your analysis, draw your conclusions, make your conjectures, and support your evidence, support your conjectures and your conclusions with data, you want to make sure that you have everything properly identified. Conjectures are actually what you're going to make beforehand, and then you'll draw your conclusions afterwards. You'll make your conjecture, and then you'll work with it. But that's not important right now. That's me going off on a tangent. So anyway, let's look at some scatter plots that we have here. Well, first of all, just before we do that, remember, explanatory, you see the letter X. The explanatory variable is the variable that's going to go on your x-axis. The response variable is going to go on the vertical axis or the y-axis. And the reason we do this is because you could think back to algebra. The x value is the independent variable. That's the one that is going to normally change at a constant rate. And we're going to see how that affects or is associated with the dependent variable, which is the vertical axis, and how that changes in relation to how the explanatory variable changes. So let's continue and let's see what we got here. All right, when you describe a scatter plot, so if I go back to this big old mess that I made, there's some key things that I want to describe within this scatter plot, and they are as follows: direction, form, and strength. You also need to know what we call a departure, and you know that as an outlier. It's called a departure because it departs from the actual shape of the actual pattern that's represented by the data, if you can discern a pattern. So you can describe the overall pattern of a scatter plot by the direction, form, and strength. Those are things that we will look at here in just a second. The direction actually will show you whether or not you have a positive or a negative correlation. The form is linear, quadratic, exponential, curved. Those are things that you look at for form. And strength is how closely are they related? Are they loosely related or are they closely related? Outliers, as always, are measurements or measured data points that are non-typical based on your full set. They might be an anomaly of some sort, something that there's a reason that that particular measured value is there. It doesn't really fit the pattern, and it's an actual measurement, but there's something that makes it stray from the pattern itself. So we have to be very cognizant of those outliers. So let's go on to the next page, and let's talk about describing scatter plots. When we look at these scatter plots, and that beautiful one that I drew for you a while ago, because I'm such an artiste, we have two ways of looking at associations: positive and negative. Positive association is an association where as one value increases or in value, or as one variable increases in value, as the other one does the same. It's almost like a direct variation, almost, when you talk about indirect and direct variation, so an inverse variation. Positive means as it goes up, one goes up, the other one goes up. Negative association means as one variable increases, the other variable decreases. That's a negative association. So let's look at this example down here. This is a relationship between the percentage of students in a state who took the SAT. And this is how they scored on their math. So, for example, in a state where 20% of students who were eligible took the SAT, the average math score was 500. In a state where an average of 83% of the students who were eligible took the SAT, the average math score was 515. So what we're looking at, this right here could be a potential outlier because you can see that it deviates. Remember that word, deviate, standard deviation. It deviates from the actual form that we see. But we're not sure, and this is where the R coefficient comes in. So when you look at this, you have to determine what kind of relationship do you see. First of all, remember we talked about shape, okay? So I'm going to scroll back up, and we talk about direction, form, and strength in addition to our outliers, right? Direction, form, strength, and outliers. So let's look back at this. Direction. This goes down left to right, which means as the percentage, the one quantitative variable down here increases, the quantitative variable here decreases. And because this is on the x-axis, we are going to say the percent of students, let me raise that a little bit, the percent of students taking the SAT is your explanatory variable, and that response variable is the mean math score. Because we're looking at this, and then we're measuring this based on this, okay? So there's a moderately strong negative curved relationship. So we're looking at the strength, the direction, and the form. Let's look at those again. Strength, direction, and form in addition to the outliers. So I can tell that there's some kind of a relationship here. I would say it's negative again because as the explanatory increases, the response decreases, okay? And you can see a little bit of a curvature here. If I were to employ my artistic skills, which I know you guys are all criminally jealous of, you can see that there's something just kind of like this. It looks almost like it may be, you know, parabolic. You know, it could be, but we're not sure. Okay, so that's basically what we're looking at when we're describing a scatter plot. So let's look at this example here. Okay, we're looking at a linear pattern here. All right, this is how many points per game a team scores, and this is how many wins. Here you would detect a positive association because as the points per game increases, the explanatory variable, I'm going to keep throwing those vocabulary words at you so that you remember them. Hopefully you don't have nightmares about them. And this is your response variable on the y-axis, on the horizontal axis. Okay, so that's a positive. It seems to be linear. And wait for it because the artiste is coming back. Check that out. Be jealous. That is a linear, that relationship appears to be linear. Now, this is a fairly small data set, so the more data you're able to collect, the more observations you have, obviously the more obvious, please don't tell your English teachers I'm talking like this. As you collect more data and have more observations, your shape and your form become a little bit more accurate. If I only have 3 observations, let's go back to this. Okay, this actually looks like a bad case of the measles. So if I clear this, if I just add 4 data points, you have no idea if that's really a strong correlation for that small of a sample. Because look what could happen. This looks linear, but what if I added all this crazy stuff? Now we're looking at something that's curved. It could be parabolic, quadratic, parabolic, you know, quadratic, whatever, same thing. Or it could be exponential. We've got to be very careful. So here we've got a linear pattern. It seems to be strong based on what we have. Boy, that's a beautiful line. I have to pat myself on the back for that one. And it seems to be fairly strong with no outliers. I really don't see any outliers in that picture. So as we move on, we're going to talk about the coefficient for R. And before you read this entire novel, we talked about this a little bit in class. It's real simple when you're looking at R. R is always between -1 and 1. So when we're looking at R, R always falls within this nice little inequality. Obviously, your poles, or your ends of the spectrum, -1 and 1, are perfect associations. So right here, the extreme values, your poles, -1 and +1, are only when it's perfect. Are we going to have perfect relationships? Probably, hardly, never. If we're looking at natural studies and nature, you're never going to have anything that's absolutely perfect. So again, it's possible, but highly unlikely. So a -1 means you have a perfect negative correlation, and a +1 means that you have a perfect positive correlation. I'm having the same issues I had today. I cannot speak. So what does it mean for R to be above 0 and below 0? Well, as we talked about, above 0 means R is positive. That's a positive association, and that line is absolutely terrible. Let's try that again. And let's use colors. Let's make positive green, and we'll make negative red. Y'all are thinking about Christmas anyway. So a value greater than 0 is positive, and less than 0 is negative. So the question is, what is considered strong and what's considered weak? Well, there's a lot of schools of thought on this, and I'm going to show you one of them. So here is one university, and this is their guidelines to what R represents. So as you can see, +1 is a perfect positive association. -1 is a perfect negative association. So now let's start moving in from the poles. 0.8 to 1.0 would be a very strong association, as would -0.8 to -1. So we're creating ranges here. 0.6 to 0.8 is a strong association, whereas -0.6 to -0.8 is also a strong association. But again, when you're looking at these, the top here, those are positive associations. So this would be a very strong positive and a strong positive. This would be a very strong negative and a strong negative. 0.4 to 0.6 is a moderate relationship. So not strong, but we're getting there. And anything from 0.2 to 0.4 is weak. And 0.0 to 0.2 is very weak or absolutely 0. If you get 0, that means there's absolutely no relationship, no association between the two. So that's just kind of a gauge for you. There's debate on some of the different people will tell you different things. Some people, some schools of thought believe that for very strong you need 0.85. Some schools of thought think that very strong is 0.75. This is a pretty good gauge right here. So let's go back to our amazing PowerPoint. So we've talked about our R. So let's move along. And let's look at these guys. What do you think? Again, besides looking like a horrible case of the measles or the chickenpox, here's examples of your correlation. Here's a 0. This is just a hot mess. Okay, this looks like my daughter's room, actually. And those are all the clothes and toys that are all over it. But there's absolutely no association. You can't discern any association there. I can't draw a line, a curve, or anything that even remotely resembles a pattern with those dots. Over here, these are getting closer. We might have something there. They're starting to kind of cluster up kind of around the same area. Here we're a little stronger. Here we're even a little bit stronger than that, and then here we're pretty strong, and here we're very strong. And again, as you look at these, this is a -3 because if you look at this, remember your explanatory variable and your response variable. See how I plugged those again? Explanatory is your x-axis, that's your dependent, and this is your response. This is a positive correlation because now, as opposed to the negative here, where as one is increasing, the other one is decreasing. Now, as this increases, so does this. That's positive. Same thing here. This is negative because as this one increases, this one is decreasing. Here, this is positive because as this one increases, and negative because as this one increases, this one decreases. So you guys are tired of hearing that. All right. Take a look. Have a heart attack. Take a deep breath, get a drink, don't faint. It's okay. This is the formula to calculate the correlation coefficient. However, rarely in AP statistics are you going to be required to do this by hand. This is all done in the mighty calculator, which I'm going to create a second video to show you how to do this in the calculator. But you're familiar with this. Remember how we do the dividing by n-1? We did that when we did standard deviation when we were coming out of the variance, correct? We're calculating standard deviation from variance. And so what these all are, these should look familiar to you. These are all individual formulas for z-scores. That's a z-score, that's a z-score, that's a z-score. Okay, that's a z-score. All of your green z-scores are your z-scores for your explanatory variable. And remember, a z-score tells you how many standard deviations off of the mean a measured value is. So let's use Christmas colors. That's a z-score, that's a z-score, that's a z-score, and that's a z-score. Those are all of your z-cores. I'm just, cutting letters off of words because it's fun to say things in weird ways. That is your z-scores for your response variables. So think of every one of these values as an ordered pair of sorts of z-scores. You basically have your axis. So if I go back up, so that I'm not rambling, let's go back up here. So what I'm basically doing is I'm pulling, for example, let's pull this data, this piece of data right here. This data that says that when you score 20 points per game, that you're going to average about 5 wins. So I have that ordered pair. And what I do is I end up calculating my standard deviation, and I figure out my z-scores for each of these. And this is my, again, this is my explanatory variable, and this is my response variable. And what I'm going to do is I'm going to pair these up, z-score, z-score, and when I get those z-scores, I'm going to come down here, and that's what this sum is each ordered pair of z-scores. This is z-score of the explanatory times factored with the z-score of the response for each ordered pair. And then you're finding the sum of all of them, and then you're going to divide by n-1. So that's how you get your R coefficient. So moving along, facts about correlation. So facts about correlation, let's just look what's in the green because apparently they think that's important in the book. Correlations require that both variables be quantitative. We've discussed that. Correlation does not describe curve relationships between variables, no matter how strong the relationship is. And correlation is not resistant. Okay, not resistant. Let's think back to that. Not resistant. Remember we talked about resistant and non-resistant measures, talking about median and mean. Remember the median is a resistant measure because the median resists outliers or data changes, and the mean is not resistant because it cannot resist changes in the data because it's directly impacted by it, whereas the median is only impacted by the location and the number of observations. So R is strongly affected by outliers. And we are going to go up and kind of look at these three, even though the green tells us these are important. Those are some cautions. Correlation makes no distinction between explanatory and response. So when I do my axes, I can actually have my response variable down here and my explanatory up here if I want to, which really doesn't make any sense, but you could do that if you want to feasibly. If you're just looking for the correlation coefficient, it's not going to matter. You got two quantitative variables that you are comparing, but that's not the proper way to do it. The proper way to do it is to actually have the explanatory on the x-axis. But if you're entering data sets, which I'm going to show you in a separate video in the Inspire, it doesn't matter which one is which. Now, when you present your data, you do want to be specific on what your explanatory and your response are. But when you're doing correlation and you're running your numbers and you're making your calculations, it doesn't matter which one is first or second, which one is the explanatory or the response. I could look at examples of, for example, car pricing. I can look at if a car costs a certain amount of money, how many miles does it have on it? If I pose the question that way, my explanatory variable is how much it costs. Because I said, if it costs this much money, how many miles does it have? So my response variable would be the mileage. So I'm comparing price to mileage. But you know what? I could switch those around and I'll still get the same R value. I could say, well, I'm going to look at the mileage on the vehicle. And then I'm going to see, based on how much mileage, what the mileage is, what's the price? Now the mileage has become my explanatory and the price has become my response. So it doesn't matter in that situation, I will still get the same R value. So I could actually have this. I could have the price and the miles. Or I could graph it like this. I could have the price here and the miles here. If it's the same data set, it's going to give you the same R. If R is 0.96 for one, up here, if you get 0.96 is what your R value is, then here your R value is also going to be 0.96. It doesn't matter when you're doing the correlation. It does matter when you're explaining your data and when we do some other calculations we're going to move on to. But for the correlation, it won't matter. You'll get the same thing both ways.